In this video, we look at the concept of instantaneous frequency. This concept is the same as instantaneous speed or instantaneous velocity. So let's illustrate using this simple graph here. Suppose this is a time of t in second, and this is a distance I traveled starting time 0. So starting time 0, suppose if I travel from my home to WSU, cannot drive in a constant speed of 40 miles per hour. If I can travel constant speed, the distance will like this. The distance will like this, straight line. But in real life, we cannot drive in a constant speed on the road. So the distance travels will be different rate of changing. The instantaneous speed or instantaneous velocity, that's we take the derivative with respect to time of the distance. You can say from here to here, almost the speed is almost constant. And from here to here, the rate of the distance increase more. So therefore, I must have accelerating. The speed of my travel is being increased. But from here to here, the distance does not increase that much compared to this period. So the speed must be slowing down. From to here, there's a deep increase of distance I traveled given this short time. So therefore, the speed must be increasing again. And from here to here, you can see the rate of the distance increase is not that much compared to this period. So therefore, the speed dropped. This is a concept of instantaneous velocity. The instantaneous frequency is the same thing. So suppose I have a cosine signal, magnitude is A, cosine psi t. Psi t, that's the angle, this cosine signal. The instantaneous frequency is I take the derivative of psi t and divide it by 2 pi. Here the instantaneous frequency has a unit of hertz because I divided by 2 pi. If I don't divide it by 2 pi, the unit will be radians per second. We do not use the unit in communication system a lot. We use hertz a lot. This is the psi t is changing with time. And if I take derivative with the time of this psi t divided by 2 pi, I will obtain the instantaneous frequency. And this is the same concept of instantaneous velocity. I take the derivative of the distance traveled with time. Now let's look at some examples on how to calculate the instantaneous frequency. Let's look at this first signal, g1 of t equals to 10 cosine 2 pi t. Note in this case, 2 pi t, that's the angle, that's the psi t, or phi of t, so it doesn't matter, whatever we call it. So the frequency, when we say frequency now, we mean the instantaneous frequency. That's 1 over 2 pi d of dt, 2 pi t. That equals to 1 over 2 pi. That equals to 1 hertz. So this is a constant frequency. And we know from before that this signal has a frequency of 1 hertz. We know that. So in this case, the frequency is constant, does not changing with time. Now let's look at the second one. What about g2 of t equals to 9 cosine t squared? And then the frequency, we always use this formula. This is a formula to obtain the instantaneous frequency. The angle is t squared. So therefore we have the unit is hertz. Now we can see in this case, the frequency is function of time. It's changing. So the name of the instantaneous frequency. when the speed is constant, that's a very special case. Now let's look at G3. G3 is 8 cosine 2 pi. I do an integral here from minus infinity to t. The integrand is yam tau. So yam tau is a function. So what's the instantaneous frequency? We take the derivative of the angle. The angle, that's this portion now. We take the derivative of the angle and divide it by 2 pi. So I put it here. M tau d tau. 2 pi and 2 pi cancel out each other. Right? So this equals to d of t minus infinity to t m tau d of tau. Here, and we take the integral, and then we take derivative with respect to time. So what we have, we're going to have mt. In this case, the frequency is also a function of time because mt is normally a function of time. It has here function of time here.